Hello everyone. Next topic is isomorphic graphs, or you can say isomorphism in the graphs. So here you are giving any two graphs, say G1 and G2, and you have to show that these graphs are isomorphic. Before going with this formal definition, let us understand the topic with the help of an example. Suppose these are the graphs given to you and you have to show that these graphs are isomorphic. Let us represent this graph G by G1, where VG1 is the vertex set of the graph G1 and EG1 is the edges of the graph G1. Similarly here, we name this graph as G2. VG2 is the vertex set of graph G2 and EG2 is the edges of the graph G2. Our first step is step number 1. We have to draw this graph as this graph, like this. Now you can see these two graphs are identical. In case you are not able to draw this graph as this, then these graphs are not isomorphic or you are not having the perfect practice. So let us check first that the graph you draw is the correct one or not. Here check. This edge A is incident to B twice, then C and D. A is incident to B twice times, then C and then D. B is incidence to A and C. A and C. C is incidence to D, A and B. C is incidence to D, A and B. And D is incidence to A and C. D is incidence to A and C. So, this graph can be drawn as this graph. They are the same graph, just the representation is different. Now, these two graphs are like identical graph. Step number 2. Make sure that the number of vertices and the number of edges are same in both the graphs. Here you have 4 vertices and here we have 4 vertices. Similarly edges 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Edges are same. So number of vertices in graph 1 is 4. Number of edges in graph 1 is 6. 1, 2, 3, 4, 5, 6. And degree sequence. So, the degree of A is 1, 2, 3, 4. Degree of B is 3. Degree of C is 3 and degree of D is 2. So, the degree sequence is 2, 3, 3, 4. 2, 3, 3, 4. Similarly for graph 2, number of vertices in graph 2 is 4. Number of edges in graph 2 is 6. And degree sequence. Degree of V1 is 4. Degree of V2 is, degree of V1 is 3. Degree of V2 is 4. Degree of V3 is 2 and degree of V4 is 3. Again 2, 3, 3, 4. 3, 3, 4. So here we have the similar properties like the number of vertices, number of edges and the degree sequence of both the graphs are same. In case they are not same, you can say that the graph are not isomorphic. 99% the graph are not isomorphic. But there are examples where these are same and the graph can be isomorphic. So this do not define whether the graph are isomorphic or not, but give you a chances. Like in case they all are similar, 99% the graph are isomorphic. But 1% when you have all the three things same, the graph cannot be isomorphic. I will show you it with the help of example later. Now here we have reached till the step number 2 where I defined you that the graph can be isomorphic. 99% surety is there. In step number 3, we start with the process of proving the isomorphism. Let us define a function f from vertex set of G1 to vertex set of G2. So there are 4 vertices A, B, C and D. And here you have 4 vertices v1, v2, v3 and v4. Now we match the corresponding vertices, like A will be matched to v2, D will be matched to v3, C will be matched to v4 and B will be matched to v1. Here A will be matched to v2, B will be matched to v1, C will be matched to v4 and D will be matched to v3. That is, f of A is v2, f of B is v1, f of C is v4, f of D is v3. Clearly, by construction, f is 1, 1 and onto. Step number 1 of the isomorphism is proved. We have a mapping F from vertex set of G1 to vertex set of G2 defined as this. And by construction, clearly F is 1, 1 and onto. In next step, you have to show that for all the edges, AB belongs to edge set of graph 1. These are all the edges. You can check the edges from here. The edges are AB and AB. I write it down twice. Then AD, AC, CD and B and C. These are all the edges in the graph G1. Now corresponding to these edges, they are image here. Like the image of this is f of A and f of V, which is equals to, now f of A is V2 and V1. F of A is V2 and f of B is V1. We have to show that for this edge in graph G1, the image of this edge FA, FV, which is V2, V1, is an edge in graph 2. So let's check here. Yes, V2, V1 is an edge in graph 2. So yes, it belongs to G2. Similarly for again FA, FB, FA, FB, we have, these are the parallel edges. So it belongs to graph 2 for these two parallel edges, this and this. Now for AC, images FA, FC, f of A is V2 and f of C is V4. V2, V4, it belongs to, yes, V2 and V4, yes, it belongs to graph 2. We will check this for all. So we had for all edges here in the graph G1, the image of these edges, FA, FB and this one, the images of these edges, these are all edges in the graph 2. We can check it from the main graph, this. Now, what you have done, you are given these two graphs. In step number 1, you made this graph look similar to this graph, like this. In step number 2, you write down all the set of vertices, edges and the degree sequence. Since they are same, there are 99% chances that the graphs are isomorphic. 1% they cannot be isomorphic. Now here we start checking if the graphs are isomorphic. So we define a function f. This function f is called isomorphism in case we verify it. So this f is defined from vertex set of G1 to vertex set of G2. A, B, C, D are the vertices in G1, V1, V2, V3, V4 are the vertices in G2. You cannot make any random function or mapping. What you have to do, you have to match the corresponding vertices. So B will be matched to V1, A will be matched to V2, C will be matched to V4 and D will be matched to V3. 100% by this construction you will get a mapping which is 1 1 and onto. So step number 3 is over. Now for step number 4, what you have to do, you write down all the edges, right, and check if the images of these edges are edges in graph 2. If this is also verified, then you say graphs G1 and G2 are isomorphic and F is an isomorphism. This function F is called isomorphism. And you are done with the question. You have to do all the steps whenever the question is asked. It's the exam. And yes, this topic is very important. Now let us get back to the formal definition. Here, G1 and G2 are the graphs given to you. As I told you in the example, these graphs are said to be isomorphic if you have a 1 1 onto function f from the vertex set G1 and vertex set G2. Yes, we had the function in the previous example. We construct it in a way that it becomes 1 1 and onto. And for all edges in the graph 1, their images are edges in the graph 2. Whenever you verified both the conditions, this mapping F is called isomorphism and the graphs are called isomorphic. Another example, like these are the graphs given to you. You have to prove that these graphs are isomorphic. Step number 1, you have to draw one graph in the form of another graph. Right? Suppose you draw it like this. 1, 2, 3 and then 4. You check that the number of vertices, number of edges are the same. The graphs can be isomorphic and the degree sequences are also the same. Then you define the function. Clearly by construction, function is 1 1 onto. For all edges in the graph 1, their images are edges in graph 2. Hence, these graphs are isomorphic. If you have to show that the graphs are not isomorphic, you can check if they do not have the same number of vertices, if they do not have the same number of edges, if they do not have equal number of vertices with same degree, or they do not have the same degree sequence, then the graphs are not isomorphic. But there are cases when all the conditions are satisfied, still the graphs are not isomorphic. For example, this. Now here, check the number of vertices. 1, 2, 3, 4, 5, 6. Similarly here, 1, 2, 3, 4, 5, 6. Number of vertices are same. Number of edges, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the number of edges are same. Check the degree sequence. इसकी डिग्री होगी हमारे पास 1, then 2, 2, 3, 1, 1. So 1, 1, 1, 2, 2, 3. Similarly here, 1, 2, 3, 1, 2, 1. So 1, 1, 1, 2, 2, 3. Now here, the number of vertices, the number of edges and the degree sequence are same. But the graphs are not isomorphic since you cannot draw this graph in the form of this graph. Or you find out a property which is not similar. Whenever I say the graphs are isomorphic, that means 100% the properties of both the graphs are similar. 100% properties are similar. If you get a single property which is not identical, then the graphs are not isomorphic. Like here, it has 1, 2, 2 pendant vertices. Vertices with degree 1, these two are the pendant vertices, but here you have only one pendant vertex. D has 2 adjacent pendant vertices here, right? But here the C has only one pendant vertex. Here you have a vertex which has 2 pendant vertices, but here you do not have a vertex which has 2 pendant vertices. Hence, these graphs are not isomorphic. Isomorphism tell you that the graph G is isomorphic to graph H if you have a bijective mapping. Bijective means 1 1 and onto mapping from vertex set of G to vertex set of H, and such that this for all edges in the graph G, their images F and FB are edges in graph H. And here you have the function of if and only if. Means from here you can go here and from here you can go here. But whenever I use the term homeomorphism, then this is similar to your isomorphism, except the point that here you have only one way operation. Like if AB is an edge in graph G, then FAFB is an edge in graph H. The vice versa is not true for homeomorphism. One another definition of homeomorphism is this. Homeomorphic graph. Suppose you are given two graphs G1 and G2. Then G1 and G2 are called homeomorphic graph if one of them can be obtained from the other by a sequence of subdivision of edges, like here. This graph can be obtained from this graph by subdivision of edges. We subdivide the edges V1 and V3 into V1, V6, V6, V3. If one graph can be obtained from the other by subdivision of edges, then the graphs are said to be homeomorphic graph. That's all for the topic. This question is asked in your internal exams. You have to show that these graphs are isomorphic. So this is the graph G1 given to you. This is the graph G2 given to you. Prove that the graphs are isomorphic as your homework.